Chapter 23, main topics. We talked about the various classes of lipids, their biological significance. There were 7 different classes. Saturated versus unsaturated lipids and how this affects their like physical properties like melting points. And then why some lipids are oils at room temperature versus solids at room temperature. Reactions of triacylglycerols, okay, hydrogenating them. So hydrogenation is done commercially for the purpose of making saturated fats, but that's also how you can end up with trans fats, which are the non-healthy kind. But we're adding hydrogen to break down the double bonds into hydrated or saturated single bonds. Okay, so that's hydrogenation. Hydrolysis. There's a whole big problem on exam 2. Was this exam 2? About write out the products from the hydrolysis of a triacylglycerol. You should get glyceride in your 3 fatty acids. We'll look at that. The difference between micelles and liposomes, that was also an exam question that we've talked over before. Glycolipids and their function, how they're planted in the lipid bilayer, and they have their carbohydrate chains that are intracellular messenger receptors. And then sterols, we talked about cholesterol, bile acids, and then sex hormones, and then the whole fluid mosaic model, lipid bilayer, all the components, and then transport across the bilayer. Those are the big ideas from chapter 23. That's a lot. Okay, so let's just begin with this question here. You guys tell me, what makes a molecule a lipid? We got 7 different classes, and they can look kind of all different from each other. So what makes a molecule a lipid?
It is one solubility.
Yes, Maggie. Okay. It's based on solubility. So the fact that it's not soluble in water, but they're soluble in non-polar solvents. Okay. That is what makes something a lipid. Now, can we name the different classes and briefly state their roles in the body? Anybody remember one? Triacylglycerols, we should all know that one.
Waxes was another one.
Yes, waxes. These are energy storage. That was the main purpose. What do waxes do?
Don't they protect the skin?
Mm-hmm. Glycerol phospholipids. You guys remember what they do? Sphingomyelins. Sterols. We had eicosanoids. And this word, I'll never spell it right. EICOSAN. And glycolipids. And these are the 7 classes, and we briefly wrote a statement about their purpose in the body. What do you guys remember about sterols? Or sorry, steroids. Cholesterol being one of those. Anybody remember any of these? Should start with the first one, glycerophospholipids.
Don't they regulate flow in cell
They're
membrane?
one of the main components in the bilayer, so they regulate flow of molecules into and out of the cell. Okay. Okay, so they regulate the flow of molecules into and out of the cell. They are one of the main components of the bilayer, glycerophospholipids. Sphingomyelins. I think of the myelin sheath on our nerve fibers. They're lipids that are a protective coating on nerve fibers. What else did we say? Glycolipids are intracellular messengers. Steroids, you've got cholesterol and sex hormones. And then eicosanoids were specialized local cell messengers. Okay, prostaglandins were an example we mentioned of those. And their response, like when you get a cut or in the blood clotting system, eicosanoids are involved in that. So glycolipids are intracellular messengers. These are specialized messengers. Steroids, we said cholesterol. And what was the big deal about cholesterol? What does cholesterol do for us?
Can't it like cause like blood clots and heart attacks?
Your bad cholesterol. Yeah, we got the HDL and the LDL, so the LDL. But cholesterol is really abundant in our cell membrane, okay, in the bilayer. And what does cholesterol help do there? Someone remembers? It increases the rigidity of our cell membrane, okay? It kind of reinforces it, adds some stability to the cell membrane bilayer. That way it's not entirely too fluid. And then we got sex hormones. Okay, testosterone, estrogen are secondary sex characteristics. Steroids produce those. Cholesterol is the base, is used to make all other kinds of steroids in the body. So we use cholesterol to synthesize other steroids that we will need. Hormones. Okay. Moving on, you will have this table on the exam resources page. But I think I wanted to use it to answer this question. The question is, why do saturated fatty acids have higher melting points than unsaturated fatty acids? So if you look at the melting points over here, this top portion, these are all your saturated, and you see melting points 44, 58, 63, 70. Then you look at the unsaturated fatty acids. These are the ones with double bonds, one or more. And look, their melting points are all way, way lower. So why is that?
Is it because in saturated fats, every carbon is saturated with the hydrogen, so it's stronger? And that the unsaturated fats has the double bond that causes a kink, which makes them less stable.
Causes a kink, stronger and stable. You're kind of getting at something. The root word, the root idea here. Anybody, Madison? That's like a good portion of it. But somebody finish that for me. What is the unsaturated and then the saturated that causes the kink, and that? What does that really get at? That causes the difference in melting points. Nothing you said, Madison, was wrong. Just maybe a little incomplete. So if we were to draw a saturated fatty acid, okay, we've got the, and then we've got this long hydrocarbon chain, and every carbon is single bonds only. So it's just this straight chain, okay? I mean, I don't know how short, it could be short or long, but it's straight. Structurally, it's straight, right? What that allows to happen is allows another fatty acid to come right up next to it. And they can kind of stack together like this. I mean, you could keep going, okay? And what that allows for in between all these, what do we know happens between long hydrocarbon chains? What kind of interactions? What kind of intermolecular forces? Abby, what did you just say?
Is it London dispersion?
Yeah, you get all these London dispersion forces all throughout the chain, tons of them. And remember, the more surface area you have, you watch Madison's Flipgrid video, she teaches you that. The more interactions you have, the more solid those things are going to be. The more forces present, the higher their melting. It's going to take more energy to break apart all those forces holding those fatty acids together because they're straight chains. But structurally, unsaturated are different. Unsaturated might look like this, but then you've got this kink, and it can start looking weird. Okay. Well, they should all be cis, right, at the end of the day. So they can start to curve around and be kinked. And how do you can't line them up with each other. All right, so the structure is completely different, and it just does not allow for this nice, compact, and all the London dispersion interactions, okay? So that is what leads to a lower melting point. Fewer London dispersion interactions between fatty acids. Okay, but those have huge consequences. And that's how we get all different kinds of oils versus solid fats, which are useful for different things. And they're useful for different things in our body as well. All right, any questions on that? So now draw the product of the hydrolysis of a triacylglycerol containing 2 oleic and 1 lauric fatty acids. Draw the hydrolysis. So oleic and lauric acid. Let's go look at the structures of those right up here. So we got oleic and lauric. So as these are written on the table, they've got the COOH group on the right, and that's fine. You can keep it oriented that way if that helps you. It really doesn't matter how you orient it on the right or on the left, as long as you draw the rest of the structure correctly. Then here's oleic acid. So the Let's just draw lauric acid down here first. What was it? C2, got 10 of those, CH2, 10 of those groups and a CH3 group. And then here's the carbonyl carbon. So first, this is going to be bonded to glycerol, right? We have a triacylglycerol, and we're going to hydrolyze it into its individual fatty acids. So you guys remember what glycerol looks like? I'm going to do it in a different color. Glycerol, you've got the CH2 and then the C and then the CH2. Okay, and these are going to be bonded to the rest of the carboxylic acid group. From the fatty acids. So then we got 2 oleic acids. This one's a little more complicated. So look at the table to see what the structure for oleic was. So 7 CH2s and then a double bond and then 7 more CH2s and then it ends. And we got the double bond. So I'm literally just copying this down from the table. Okay, so there's 2 oleic acids and a lauric acid. And the biggest part is that we have connected the carboxyl group to glycerol. This is a full triacylglycerol. And the red are your fatty acids that you get from the table. Okay. When these bind, what we're about to do is hydrolyze. Okay, draw the products of the hydrolysis. So when we're doing hydrolysis, we're using a water molecule to break these apart, right? Any hydrolysis reactions using water to break molecules apart. So we'll say plus water. And what's going to happen is water has H and it has OH. This is what we commonly see anytime we hydrolyze esters or amides with water. Same idea. Anytime you hydrolyze peptide bonds or glycosidic bonds, the OH is going to go to one part and the H is going to go to another part. So we're going to break bond connecting the fatty acid to glycerol. Sorry. It's going to be this bond. I get those messed up sometimes. Okay, regardless, if you get it mixed up on the exam, if it happens, then just remember you should end up on with the same products because you're adding water back. And so you shouldn't, honestly, either way, you should write the same products. Okay, so in this case, the OH is going to come in, it's going to bind to the carbon. And this is going to happen 3 times. The hydrogen is going to bond to the O from glycerol. Okay. And that's going to happen literally with every single fatty acid. So when we break these apart, what we get, I wonder if I can copy and paste this. So you end up, when you break that bond, your fatty acid looks like this, okay? So the OH, well, this part broke off too. Looks like this. So the OH is gonna come from water, gonna come and bond there, and you've restored, this is your carboxyl group, your carboxylic acid part. That's that functional group. And this is why we call it a fatty acid. And that's going to happen for both oleic acids and lauric acid. So we would need to draw this essentially 3 times. So I'm going to see if I can copy and paste all of this. So draw all 3 fatty acids, and then we've got to also redraw glycerol. Okay, so there's lauric acid and 2 oleic acids, and now glycerol. I'll do it in blue since it was in blue. And these hydrogens are from water. Okay. So that is the hydrolysis of a triacylglycerol. We're using water to break apart the bond between the carbonyl carbon and the kind of the ester oxygen. You see how this is like an ester functional group right here? So we're breaking that ester bond. And then the OH group binds to the carbonyl carbon, the hydrogen bonds to the oxygen from glycerol, and you get your 3 fatty acids in a molecule of glycerol, okay? All right, any questions on the hydrolysis of a triacylglycerol? All right, we talked about this just above when we mentioned all 7 classes and wrote out their functions. Glycolipids specifically though, remember they're in the lipid bilayer. So if we've got a lipid bilayer here and all our hydrophilic heads and the hydrophobic tails, and that's on both sides, remember. So these glycolipids are tucked into the lipid bilayer. I'll just draw a picture of one here. They're fats, but then they have these sugar parts. So pretend that each of these black spheres here are is like a monosaccharide, and they can be polysaccharides. Like it can be chains of monosaccharides that are sticking out above the bilayer into the intracellular just environment. And these are receiving messages that can, do all kinds of stuff inside the cell, relay information for transport. But that's where they're found in the body, in the lipid bilayer, and then they protrude out above the bilayer. Okay. What are the role of biosalts? Okay, biosalts are types of steroids. Biosalts, what did we mention with biosalts? Anybody remember? I want y'all to tell me now.
Is that like stomach acid?
No, this is to do with your gallbladder. So after the stomach, when we get into the intestines, the gallbladder is there. It's got biosalts that can be released into the intestines to aid in the final stages of digestion for lipids, for fats. Okay, we need some extra help digesting fats, because remember, fats don't just fall into a polar hydrophilic environment, because they are philic environment. They're very hydrophobic. Their hydrocarbon tails are. So bile salts help. How do they help?
Fats.
What was that, Claire?
Don't they emulsify the fats?
They're emulsifying agents. Yep. Emulsifying agents, okay? How is that? Well, let's just look at a picture of one really quick. I'm gonna scroll down, sorry. Okay, here were two pictures of bile salts. Cholic acid, chenodeoxycholic acid. But what you see, what you should notice, and what I've circled and I'll also highlight are these OH groups. We've got some polar groups, and we've got this carboxylic acid here that make this molecule. It's got both polar properties and non-polar properties. That's how it's an emulsifying agent. So the polar groups interact with water in the polar environment, and the non-polar portion of the molecule can interact with and bind to the fatty acids and help bring them into this polar environment of our bodies, and the aqueous environment of our blood and our cells and our intracellular and the cytosol. So that's what bile acids do. They help keep fats from just clumping up together and help break them apart so that they can actually mix and go places in the body. And you've got to have properties, both polar and non-polar, to do that. Okay. And that's what we said in the small intestine. They exist in their anion form, referred to as bile salts. They contain more hydrophilic portions. They can aid in the formation of micelles. They essentially are emulsifying agents, so during digestion. Okay, so that's bile acids. That's the main role, is that they help in aid digestion. The main thing I want you to take away. Okay, last two questions here. Name the model that represents the overall structure of the bilayer. We'll ignore that. We kind of need to get to the other stuff, so we'll just answer that part. And then the various kinds of transport across the bilayer. I'll let you go back and add an example of a molecule, but we'll at least name the kinds of transport. So what was the model that we said represents the bilayer? Anybody? Fluid mosaic model. Why is this a good name for it? What does fluid and mosaic allude to?
Isn't it like just a mix of, I'm forgetting the word. Like I know it, but I don't. It's like a mix of things, right?
Eclectic, or there's a lot of different things in the bilayer. Yes. What things are in our bilayer? Like a mosaic is a piece of art with lots of different kinds of things in the art. Could be different mediums, different whatever. But here in the bilayer, kind of have a conglomeration or a mixture of what things?
Is it fats and proteins?
Mm-hmm. We have the fatty acids. Okay, specifically the glycerophospholipids. That would probably be better to write. What else? Oh, Madison said proteins. All kinds of proteins. We've got some that are channels, some that are gated protein channels, some that are not gated, some that are just peripheral proteins. We have cholesterol in there. And so we have a mix of things, which makes it a mosaic. And then it's fluid, okay, because things can move through it. It's not super rigid like a brick wall. It can move and adjust, but it's not too fluid at the same time. All right, real quick, the various kinds of transport. There's 3 kinds. Who remembers one kind?
Is this like active? Is that the one? Okay.
Active transport.
Was there a simple diffusion?
Simple diffusion,
And passive transport.
Simple diffusion is a kind of passive transport.
Oh, okay.
What's the other kind of passive transport?
Is it
Something that
facilitated?
facilitated diffusion, Okay, so this is also passive transport. So what's the main difference between active and passive transport?
Doesn't active require energy?
Mm-hmm. And I'm not going to say every single time, but active transport can pump molecules against a what?
Against a gradient?
Yes, okay, whoops. Molecules or ions against a gradient. Okay, remember a gradient is a concentration difference. Think of the proton gradient in oxidative phosphorylation. You've got a lot of hydrogen ions on one side of the membrane, very few on the other. Gradients are useful because they direct the flow of molecules. They tell molecules how to move across a membrane. And in passive transport, molecules move according to the gradient. In a gradient, molecules move from high concentration to low concentration. Okay. From high concentration to low concentration. And passive transport requires no energy and molecules move according to the gradient. In active transport, molecules can be transported against the gradient to maintain the gradient. All right, that's chapter 23. Questions on any of that? Well, we'll jump over to review 3 then. You ever played Kahoot in a class before? I wish I would have had time to make this into a Kahoot game, but maybe for a future class. It's a lot of fun. I'd always do it for bonus points, especially for those competitive souls. Anybody super competitive? I want to hear from y'all.
That's a
Who do you?
no.
You're not competitive, Cameron? Yes, you are. You play sports. How are you not competitive?
I'm not competitive at everything.
Okay, fair enough. I could care less about golf, but I'm super competitive at card games. All right. Robin, I feel like you would be competitive. I don't know why I'm saying that. Robin?
I am. I'm here. I was trying to get my microphone, but
Okay. Chapters 18, 19, and 21. So proteins, enzymes, and biochemical energy, which was my favorite chapter, 21. Proteins. All right. So we talked about protein function. What do? They're the workhorses of our body. They do everything. But we said they provide structure support. We have structural proteins. We have some proteins that aid in hormone function. We have proteins, obviously, that act as enzymes. All enzymes are proteins, so they have catalytic activity. They make reactions happen. So we have different kinds of proteins that do different things, and we mentioned that. And then parts of an amino acid and classifying them according to side chains. That was one of the big parts, okay? The big parts, and then the 4 levels of protein structure. Peptide and peptide bonds. I mean, that was a quiz question. I know you had identify a peptide bond. So I want you to know in a strand or string of peptides where you would break them apart into individual amino acids. We talked about the idea of simple versus conjugated proteins. Conjugated proteins have some sort of added non-protein element, like a sugar or a lipid, which a glycolipid is a conjugated protein. You could have heme proteins, metalloproteins that have metal ions in their active sites or at different places. So those are conjugated proteins. It just helps aid the function of the protein. Simple proteins are just amino acids only, no added elements. And then protein hydrolysis, okay, which kind of, again, goes back to knowing where the peptide bond is and where to break it. And then protein denaturation, okay? So we'll talk about the enzymes that do protein hydrolysis when we get there, and then the items that could, or the things that can lead to protein denaturation. All right, so here's just some questions. Let's draw the amino acid leucine. Label the alpha carbon, the side chain, and then the amino and carboxy terminals, or the N and the C terminals. Leucine. So if you are not sure, remember, I'm going to remind you, you have this table of amino acids in our lecture, and you just go back and boom, there's leucine. So let's draw leucine. So that's how it would look at pH 7.4 if it's by itself. The N and the C terminals are charged. So go ahead and label the alpha carbon. Indicate somehow what portion is the side chain. And then which terminal is which. So here's what you should have. This right there is the alpha carbon. And this is your N terminal. This is your carboxy terminal. And this right here is your side chain. So all the different parts. Now remember the alpha carbon, I'll put a big blue box for every amino acid. This part is the same. This part does not change. It looks identical, but what changes is the side chain. Side chain is different. Amino acids. Okay, next question. What kind of amino acid is leucine, and what kind of amino acids would you expect leucine to interact with in a protein? So we can classify amino acids. Are classified according to what part?
Polar, non-polar.
Polar, non-polar, those are two types of classifications. And which part of the amino acid are we looking at when we're deciding what kind of amino acid it is?
The side chain.
The side chain. So is amino acid polar, non-polar? There's two other types of classifications besides polar and non-polar.
Isn't it non-polar and it would react with non-polar?
Correct. So leucine is non-polar. Okay, all you have is hydrogens and carbons. Okay, so it's non-polar, and it would we would expect for it to interact with other non-polar amino acids. Okay, so leucine could interact with isoleucine, glycine, valine, alanine, phenylalanine, tryptophan. There's a whole group of them. If you look at the table, it can interact with any of those. Okay. Go back to your leucine amino acid and add the amino acid cysteine to make a dipeptide. Identify the peptide bond. Well, the problem is when I wrote this, I didn't realize I would write all over leucine. So if you need to redraw leucine, do it. I'm just going to erase a little bit. We are going to make a dipeptide with cysteine. I'll do cysteine in black. So what happens when you make dipeptides? So let's go find cysteine, because we got to draw cysteine correctly, right? Well, cysteine is down here in the polar group. So there's cysteine. So we're going to draw him attached to leucine. So how do we do this? Anybody? We're going to take that negative off right there. What should we do? I want somebody to help me out here. What do y'all think? So full amino acids, when they're neutral, look like this, NH2. At physiological pH, yes, the amino group is charged, NH3, okay? But I'm gonna draw it neutral here on cysteine, just to show you what happens when peptides join together, or amino acids join together into a peptide. So what's going to happen is we are going to lose one hydrogen from the amine group and this OH. So we're going to dehydrate. These are often called dehydration reactions. Dehydration reactions are often the opposite of hydrolysis. CH2SH, and there's, okay, so there's cysteine. And we're going to lose the OH from leucine. You always lose that from the N-terminal amino acid, and you lose the hydrogen from the amino group of the C-terminal amino acid. I'm saying C-terminal because cysteine's the one on the right. N-terminal because leucine's the one on the left. So then we could let's see if I can make this work. Slide this over, and that is, I gotta add one hydrogen back on right there, because we only lost one hydrogen from that amine group. We still have one hydrogen on that nitrogen. Okay, and here's your peptide bond right there, linking those two amino acids together now. Okay. All right, could you keep doing that? Could you draw a long chain of amino acids? I'm not gonna make you draw a really long one. All right, there's your peptide bond. Any questions on that one? Okay, can we state the 4 levels of protein structure and the interactions that stabilize each level? I'm gonna do something I've never done. I'm gonna call on people. Y'all are so quiet. Cassidy, help us out with the first level. Do you remember what we call it?
No.
Okay, I'll allow one tag or one phone a friend. What friend do you want to phone?
Claire.
Okay. We're talking about, okay, are we talking about like primary structure? With that?
Primary is the first level.
Okay, cool. And
Okay. So we got that. Okay, now I'm gonna call on somebody else. What kind of interactions stabilize each level? So what is, let's define, what is primary? The primary structure of a protein, what makes up that?
Is it the sequence of amino acids?
Boom, Madison, it is the sequence of amino acids. Okay. Now, I'm gonna call on somebody else to help me figure out what kind of interactions stabilize. Well, okay, we actually don't have stabilizing interactions here yet. It's when we get to the secondary level, we start to see some stability. Okay, so what is this? What is the next level called?
Is the next level where we have like the beta sheet?
Alpha helices, beta sheets, we'll start to see those because of the interactions that stabilize secondary structure. But what do we call it? Well, I just said it. Secondary structure. So we got primary, then we got secondary. So secondary, so primary structure is just the sequence of amino acids. And this is critically important. Remember, one flaw or mutation or interruption in primary structure can lead to diseases, and it can lead to loss of protein function. They can have major consequences. Secondary, what makes up secondary structure? Okay, so this is where you'll see what Abby was alluding to, alpha helices and beta sheets. Okay, now how do we get alpha helices and beta sheets? There's different interactions that are holding the chain, the sequence of amino acids into these coils or into these sheets. So I'm going to call on Robin to help me figure out what kind of interactions do we see at the secondary level.
The secondary?
Secondary level, what kind of interactions hold together our alpha helices and our beta sheets?
Okay, I'm not gonna lie, I really didn't get into those interactions. I didn't really learn. I didn't.
Okay, you can phone one friend. Who do you want to throw under the bus?
I don't know.
Who do you want to pull under the bus with you?
Why am I having to go under the bus? Why am I
You don't have to go under the bus. I'm kidding. You're not under the bus, Robin.
Okay. I mean, I remember the interactions, but I don't know. Hold on. There was hydrophobic, hydrogen, disulfide, salt bridges.
That's I just said it's the next level.
What do you mean?
Those are the next level of structure. We haven't gotten there yet.
Oh, okay, okay. What was before that?
Secondary. Alpha helices, beta sheets. What kind of interactions stabilize the protein at this level?
Oh my gosh, I don't remember.
Okay, anybody want to jump in and help out?
I think the beta sheet is between hydrogen bonds, isn't that?
It is hydrogen bonding specifically between what kinds of amino acids? So hydrogen bonds between
Is it
Backbone.
between itself?
Maggie. Between, did y'all hear her? Say it again, Maggie.
Backbones.
Backbone atoms. Okay. So let's think about this. I'm actually going to jump over to the lecture where we talked about this. So there was primary structure where we just said the primary sequence is the amino acids. Okay, linked by peptide bonds. All right, here's secondary structure. Let me erase a whole lot. So we said the secondary structure, regular and repeating structural patterns such as alpha helices, beta sheet, created by, here's what I'm talking about, hydrogen bonding between, that's what Maggie said, backbone atoms in neighboring segments of a protein chain. So here's a picture, because I like pictures, visual pictures help me. So here's protein chain number 1, and you see the primary structure. You see these are the alpha carbons of each amino acid. And then you see the nitrogens, and then you see the carbonyl carbons, okay? And these dotted lines, so between the carbonyl, the oxygen of carbonyl group from one protein chain, and then the hydrogen on a nitrogen, you get backbone, you get hydrogen bonds between those backbone atoms. So this is the backbone, and then the atoms branch directly off of that, which we also consider to be part of that backbone. That's hydrogen bonds between those. So here would be another one. That is what stabilizes beta sheets and alpha helices. Here's a picture of an alpha helix. And all these little red dots indicate, and they show you hydrogen bonds. So the red atoms are oxygen. All right, and this would be the carbonyl carbon on the backbone. This kind of gray ribbon is the backbone, and it's kind of spiraling. So the oxygen here is interacting with, looks like a nitrogen there, or a hydrogen bonded to a nitrogen, sorry. By the way, there's a color, there's a whole key to tell you the color coding of each atom. So if you really take some time and look into this, you can see there's a whole bunch of red dotted lines holding alpha helices together. And these are all hydrogen bonds between just backbone atoms, okay? And this picture, figure A right above this, is just showing you how it spirals around and makes the helix, okay? And then over here, B, it's showing you how these R groups, all the green are the R groups, how these are sticking out on the sides, okay? So we'll get to the R groups and those interactions at the next level of protein structure, but at the secondary level, you have these regular repeating patterns, and you have hydrogen bonds between backbone atoms. Same idea with the beta sheets here. With beta sheets, you have 2 or 3 or 4 more chains of just different peptide chains, and you're getting hydrogen bonding between the peptide chains, between the backbone atoms of between peptide chains. In an alpha helix, all the hydrogen bonds are occurring within one chain. But in a beta sheet, it's occurring between 2 different chains, holding chains together into a sheet. Okay. What's the next level?
Tertiary.
Yes, tertiary. I think I heard more than I heard Madison say that. Tertiary. And tertiary is when you have so we know proteins You have the primary sequence of amino acids in this chain. And then the chain begins to fold together into alpha helices and beta sheets. But when the chain is fully all folded together, it can kind of look just like a wad of spaghetti. Okay, it looks very disorganized, but it's full of structure and it's full of intentional interactions. When that chain is all coiled together in its active form, that is the tertiary structure. Okay, so it is the folded protein chain. Okay, it's the chain folded into its active form. And what is holding that together? What's keeping it from just unraveling back into its primary structure? What are the interactions that stabilize this level?
Robin, here's your moment.
The disulfide.
That's one of them. Okay, these are interactions between,
Oh, it's between the two cysteine.
that one is, but specifically all the different types of interactions are between side chains. Okay, between the R groups or the side chains. So now there's 4 kinds that can happen between side chains. Robin said one of them, disulfide. And she said that these occur between 2 cysteine amino acids, and she's correct. That's one example of an interaction that holds proteins together at their tertiary level. So what's another? There's 4 examples.
Is Saltbridge one?
Salt bridge, thank you, Maggie. These occur between acidic and basic amino acids. Because you got the plus charge and the minus charge, and those are, okay, the acidic have a negative charge. The basic amino acids have a plus charge on their side chain. So those electrostatically are attracted to one another. Okay, there's 2 more.
Isn't hydrogen bonding one?
Hydrogen bonding is one. Okay, these occur between polar amino acids that have polar side chains. Okay, so threonine, tyrosine, serine. I mean, you can go look at that polar section. Any of those can hydrogen bond. Stabilize tertiary structure that way. And then what was the last one?
Hydrophobic.
Yep. I don't know who said that one, but good job. And this occurs between amino acids with phobic side chains. Okay. So to remind you, the picture for this, I'll be right back to the slide. Some of you may still be writing it now. Scroll on down. Here was a picture. I really like this picture from your textbook. It gives you this protein strand that is coiled and folded into its active form. And then it shows you examples of all the different kinds of interactions. And we have them listed over here: hydrogen bond, salt bridges, disulfide, hydrophobic. So you can see the parts that are highlighted yellow. These are pockets where there's clusters of side chains that are all hydrophobic, all hydrocarbons, and they're interacting. So this would be a hydrophobic, water-free pocket of the protein. But then you can also see where you have these backbone atoms. You can get interactions even at the tertiary level between side chain and backbone atoms. But hydrogen bonds between peptide groups. So peptide meaning these are groups on the backbone. Backbone can still interact with each other to help stabilize tertiary, but those are the primary dominant things that stabilize secondary. You can also get hydrogen bonds between the side chain. So here's a tyrosine side chain, and it's interacting with via a hydrogen bond with a backbone atom. Okay. And then right up here, you have lysine. It's got a positive charge on its side chain. It's a basic amino acid. It's interacting with what looks like aspartate. It's got a negative charge on its side chain, so that's a salt bridge. So all the different kinds. And then you can see these red dots holding what looks like a pleated beta sheet together. See, these are the hydrogen bonds holding the beta sheet together. They look like a ladder. You climb up those. And then you also can see all the hydrogen bonds holding alpha helices together. So it's showing you secondary structure and the interactions that hold those. Oh, here's a disulfide bond, like Robin was saying, 2 cysteine atoms. Okay, so I like this picture because it just shows you all the different ways those can happen. Okay. So there's a lot going on there at the tertiary level. Did I miss the joke? Cassidy's smiling. Okay. Last one. Quaternary protein structure. Abby, you got to share now. What's so funny?
Can't.
Yeah, okay. All right. Quaternary level. What makes up quaternary protein structure? Robin, I don't know if we're gonna be done at 10:45.
I didn't think we would be, but it's okay. I'll just rewatch the last bit of it when I get back from my doctor's appointment.
Okay.
Do you think it'll be up by then? Like, when do you think you'll have it up today?
I mean, yeah, as soon as it tells me that's the link is ready, I'll get it processed on YouTube.
Okay, awesome. Because I'll have to get off here at like 10:35 at the latest.
Is it a bunch of 3D things together?
This is where you start to get folded protein chains in their tertiary structure, and then you have multiple chains bonded together. So hemoglobin, collagen were examples of proteins where we said they have really dynamic quaternary structure. I'll say multiple folded on it together. So primary kind of looks like that. The amino acids are held together by peptide bonds. I guess we could say the type of interaction that stabilizes this would be peptide bonds. Technically. Then you have these begin to coil into alpha helices or pleated beta sheets. And then you get this whole big wadded thing that might have some alpha helices in it. And then at the quaternary level, you have another one. I'll draw it in a different color. And it's interacting, these two chains are interacting with each other and they're held together, okay? By hydrogen bonds and salt bridges and all kinds of things. But these two chains are held together and that stabilizes the quaternary level. And it can be any of the types of interactions that hold together tertiary structure. It could be hydrogen bonds, it could be hydrophobic interactions, it could be salt bridges. Okay. Okay, so that was quite a bit. Primary structure or protein structure is, there's a lot to it. Any questions on protein structure? The levels of protein structure, we didn't even do this. The next part, specifically for tertiary structure, provide example of amino acids that would participate in the various types of interactions. Obviously, what we did for disulfide, we said cysteine, add amino acids. Salt bridges, we said acidic or basic. So that would be your lysines, arginines, aspartate, glutamate. Hydrogen bonding, anything polar. Same for hydrophobic. Anything anything non-polar for hydrophobic. Let's try to keep going. Y'all please slow me down though if you have questions. Give 2 examples of conjugated proteins. So I don't mean you have to specifically say the name of the protein, but 2 kinds of conjugated proteins. Anybody remember types of conjugated proteins?
Isn't heme one of them?
You can have hemoproteins. You've got these heme groups that have iron in them.
I think there was a metal group too, wasn't there?
Yes, we call those metalloproteins. Contain a metal cation. So in the electron transport chain, cytochrome C is a great example of this because it contains the iron iron +3 that is reduced to +2 when it's passing electrons. But that's an example we talked about in electron transport of a metalloprotein. Okay, you've got glycoproteins that contain carbohydrates. You've got your lipid proteins that contain lipids. There's a whole table right here. All right, those are all the different kinds. I might jump over these. Well, real quick, we're almost done. Let's skip over this problem right here. Let's do this one. What kind of enzymes hydrolyze peptide bonds? What do we call enzymes that hydrolyze peptide bonds? Proteases. Okay. So proteases hydrolyze peptide bonds. Do you guys remember any particular kinds of proteases?
Was chymotrypsin one?
Chymotrypsin.
Trypsin?
Uh-huh. There's one called carboxy peptidase that cuts off the amino acid from the carboxy terminal. There's pepsin, which is active in our stomachs. Okay, let's discuss their specificity. So I just said carboxypeptidases cleave off the amino acid from the C terminal, carboxy terminal. So they just cut off the carboxy terminal amino acid, the one furthest right. We always put the C terminal on the right. Okay, where does trypsin cleave?
The carboxy terminal side of lysine and arginine.
Mm-hmm. C terminal side of arginine. Then chymotrypsin.
Cleaves the carboxy terminal side of aromatics.
Mm-hmm. Look at Abby carrying the team. One time, so I have one of my best friends. She didn't live in Arkansas anymore, but this was so funny. They're like, she's married now, but this was when she just got married. And her husband were doing some kind of like activity with at her workplace. They kind of like had an employee get together thing. And it was going to be a competition. So they paired them up with their spouses. And she goes, her husband's like super quiet. She goes, he looked at me and he said, I better not have to carry you through this. And she interpreted that as like, you're calling me fat. But what he meant was like, he's just competitive. Like, I better not be carrying the weight of our team. And she goes, we didn't talk about it the whole time. And at the end of the night, we got in the car to go home. And I was like, so can we talk about how you called me fat? And he was like, what are you talking about? Anytime I say that, I think about that story. Better not have to carry you through this. Okay, so that leads us right into this next question. What fragments are produced when chymotrypsin acts on the following peptide sequence? Okay, what fragment? So where would we cleave? We said chymotrypsin cleaves on the carboxy terminal side of aromatics. So which ones are aromatics?
I'm trying to do it without looking, so I could be wrong. I don't know the name of it, but I think it's the pro one. Is it the pro?
Proline is not aromatic. It does have a closed ring structure.
Tyrosine.
Yep. One more.
I don't know if I'm going to pronounce it right, but it's the PHE. Is it phenylalanine?
Phenylalanine.
Yeah, phenylalanine.
Phenylalanine. Yep, so it'll cleave there and there. So we'll get ASP and TYR. Then PHE would be a fragment. And then the rest of this would be a fragment. Okay, what about what trypsin acts on this right here? So you're going to find all the lysines and all the arginines. You're going to cleave directly after those. So boom, it should cleave there. ARG is arginine. So this would be fragment number 1. This would be fragment number 2. That would be fragment number 3. Okay. I'm going to jump over the protein denaturation. That's at the very bottom of your slides that you'll probably have. So just look over those and know what agents can cause protein denaturation. And that gets us to enzyme. So why don't we take a break? We've been going strong for an hour and a half now. And then we'll come back. Let's come back at 10:45. So here in about 20 minutes. And we'll knock out enzymes. And we'll do as much as we can on biochemistry, or sorry, biochemical energy. And hopefully we can get that done within 45 minutes to an hour if we're moving. But then we will really have reviewed all the chapters except for stuff, material on exam 4. And we did not swing back around, and we had 2 chapters, I think, at the end of our very first review that we did not explicitly go over, but I encourage you to look at those questions and let me know if you have any thing you need to ask me on those 2 chapters. So let's take a break. I'll see you all at 10:45.
Okay, I won't be back on.
Okay, Robin, we hope your appointment goes well.
Thank you, but I'll see you tomorrow.
Okay, I'll see you tomorrow.
All right, bye.
Bye.